when you're dealing with interacting gravitons are a nightmare, right? I mean, just it's just a mess with traditional ways. So that's why, I mean, there are things that you just couldn't do before that now you can do because you can do the gauge calculations. So a lot of what I care about is gravity, but a lot of what I care about is efficient calculations of gauge theories, which is also a big pain in the ass. And
expected to see more like QCD, higher order.
yeah, well, so the thing is, I mean, so there's a block that actually is after the integrand, which is integrated. So some of these integrals at like 3 loops and higher, we still don't know how to do yet, right? So that's, there. If you look in the literature, there's a ton of 1 loop stuff. There's a handful of 2 loop stuff, and then there's nothing at 3 loops and higher in anything other than the simplest theories. And so, yeah, but we have aspirations. So that's I mean, I think if I was looking for I'm sure I'm mic'd right now, but if I was looking for wins in the near future, some of what I'm doing is some of what I'm doing is classifying effective field theory operators using this sort of color dual structure, and hopefully I can talk a little bit about that by the end of today's lecture.
Cool.
Yeah.
I did, it was fun. The UI is so bad.
I usually do it on
Oh, there you go.
You can see all 8 next to each other.
Oh, the octurtle?
Yeah.
Yeah. Oh, it's so relaxing relative to Wordle. Wordle's stressful. You've got like 1 shot and well, I mean, it was fun until these nightmare occasions where you get like everything except for 1 in the first one, and there's more redundancy than.
Sometimes it's a mistake to try to get the answer too soon.
Right. And I absolutely agree. Sometimes going too quickly to the answer is just a mistake.
I watched a YouTube video about someone trying to find the optimum guessing.
Mm-hmm.
Well, I guess we should. All right, good morning, everybody. Let's get going. So we've got just a half day today. So we're going to first have John Joseph finishing up talking about scattering amplitudes.
Yep, today I'm finishing everything you could care about scattering amplitudes. Well, at least I'm going to finish what I'm talking about. So at the end of last lecture, we saw the emergence of gauge invariant objects that were smaller than full scattering amplitudes for gauge theories. And how did we do this? We went to a minimal color basis that was relevant to the theory, and then whatever's sitting next to independent basis pointing in different directions in color space has to be gauge invariant, right? And they're called ordered amplitudes because what's sitting in front of them maintains the same color order as the color weight in front. And so what I was asked at the end, and what I'm going to start with today, is how can you identify all the graphs that contribute to a particular color order? All right, so lecture 4. Okay. I hope I get to this, but I'll definitely be getting through these. All right. So the notion of ordered graphs, ERED graphs, is critical for efficient gauge calculations. Now, whether or not you love Feynman rules or you don't love Feynman rules, you don't care about Feynman rules, if you're going to be calculating gauge theories, you want to calculate in the smallest building block that's gauge invariant possible, because you can bound any errors you make, and you can verify you're building things correctly, right? So it breaks a monstrous problem to something that's very reasonable. It breaks a problem that scales factorially into something that scales exponentially, that if you've written down functionally, then everything else that was in the factorial expression, you just get by relabeling. I'm going to talk about how to build ordered amplitudes in two ways. The first is less efficient, but very clear that you're never going to get something that breaks your color order. Okay? And the second is also very clear that it never breaks your color order, but more iterative. All right, so I'm going to introduce the notion of operators that operate on graphs, and all they do is they change the connectivity of one edge. Okay? So if I have a graph where I could have all sorts of stuff happening off of A, and stuff happening off of B, and stuff happening off of C, and stuff happening off of D, and this could be in the middle of some multi-loop diagram. It doesn't matter, I'm just focusing on an edge. And you can specify an edge by specifying the two vertices, the connectivity of the two vertices that connect it, right? So in this case, I've got ABE and ECD, okay? If I was labeled with color, if it was momenta, then minus E, my outgoing convention, whatever, right? So my color preserving graph operator is called t hat, right? And it's named like that because what it does, when you've identified an A, B, C, D, is simply connect B to C and connect A to D. Okay? So I've got some edge embedded in some graph, right? And I'm going to leave everything else the same, but I'm just going to change the connectivity around this edge, and I'm going to get, yeah, go for it.
What if that process isn't kinematically allowed, since we're only dealing with on-shelf?
Good. So the conversation I'm having right now, as I started with last time, and I should have mentioned this again, is I'm starting with adjoint, stuff in the adjoint, so all channels have a right to show up, okay? And then you can you can play this game, and then you can always take restrictions for channels that aren't allowed to show up if you've got flavor considerations, right? So this is the most complicated case. I mean, glue is complicated. Gravitons are complicated, glue is complicated, right? But when you can handle it, when you can make it as easy as possible, then other stuff's easier too. All right, so and I hope you can see that I could have a real weird looking graph like this, right? That's about as weird as I can have for an edge, right? So what do? You straighten it out, you identify these, right? And you apply a t-hat operation to get something like this, yeah? Good. So what does this look like on like a 5-point amplitude? I'm going to do t-hat right here, okay? A, B, C, D, E, A, B, C, D, E. It maintains color order. There's no way for this operation to violate color order, and it cycles through all the graphs that have this. So if you apply t-hat till closure, keeping all graphs and just going around, if you apply t-hat till closure, you'll get all the graphs that have the same color order. Yes, question? Oh, good. All right, so this was t-hat. And so how about I instead, all right, what I'm going to do, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, but now I'm going to map to here. So I'll call this A, this B, this C, and this D. Okay? Now, what am I going to do? I'm going to connect A and D. A and D. And what am I going to connect? I'm going to connect B and C. B and C. This is a 2 here. Right? And I've got a new edge that's connecting them. So this is a distinct graph. Right? If I was to draw it to look like this, right? 1, 2, 3, 4, 5. Right? That's, yeah? Okay, good. So you just do this till closure. And so you do it on every edge of every graph you get until until you've touched every edge once with your t hat, and you're done. Okay? Cool. That's all I want to say about that. So I'm going to mention there's another operation you can do. That other operation would be a U hat. Okay? And what does that do? It brings A and C to touch, and it brings B and D to touch. Yes?
Does the number of vertices always have to stay the same with T and U?
Yeah. So 1, 2, 1, 2, 1, 2, 1, 2. Yeah. Number of vertices, number of edges, everything's. I'm not. Okay. So the T hat. Do you guys ever play a game that looks with like the paper that looks like a gravitational wave, right? Right. So that's what T hat is. Okay. So it maintains the order. It doesn't. It never changes the order. So you stay planar, right? You stay in a plane with T hat. So yeah, you stay in a plane with T hat. You leap out of the plane with U hat. Okay. Good. All right. Anyway, so to get color ordered graphs, you could just start. If mostly. So let's pretend that mostly what was relevant to many experiments is tree level. So you just write down something that's obvious, n minus 2, n minus 1, and something that's obviously planar with the right order. And you just apply t hat till closure. Okay. What's inefficient about that is unless you have an algorithm that doesn't ask you to, if you keep touching the same, is this graph isomorphic to a graph I already have? Do I already have this? Do I already have it? That's not spectacularly efficient. Okay. So what's something that's more efficient is to just start at 3 point. All right. So 1, 2, 3. Okay. And the idea is you add your n plus 1 leg to every edge to the left of n, left in this sense, and the right of 1. Okay? So I have 2 options, right? So I'll do them both. 1, 2, 3, 4 over here, right? And 1, 2, 3, 4. And so remember, these are graphs with structure. You care about the order around vertices because you're talking about gauge theories, right? And so this notion. So what I meant left, I should have called that clockwise, right? And to the counterclockwise of 1. Okay? So let's do that one more time to these. All right? Simplest one first will be this graph. So there were 1 at 3 points, 2 at 4 points. So I can go on either 1 or 5. So 5, 1, 2, 3, 4, or 1, 2, 3, 4, 5. Okay. Now I have 3 options over here. 5, 1, 3, 4. 4. Five, 1, 2, 3, 4, and oh, let me put this guy over here. 1, 2. I'll get out of the way so you guys can see what I did in a second. 2, 3, 4, 5. Okay, and so we have the five graphs of 5. Yep, go for it.
In the top row, do you not need to add an external like to 2 because that would be sort of what we showed at the end of last class, where you can make adding external like to 2 out of these 2 guys?
So we're considering the ordered graphs that maintain color order, okay? So what are these 2? Let me redraw these 2 graphs in a more familiar way, the way I've been drawing them. So I'll call this A and this B. Or I should call this, T and this S, but I'll call it A and B. So A, 1, 2, 3, 4, and B, 1, 2, 3, 4. Okay? And so these are the 2 graphs that contribute to the color order 1, 2, 3, 4 at 4 point. Right? So what if I wanted, 1, 3, 4, 2? Then what I do is I literally just relabel. I'll take so. Right? I just and I get the correct color order for 1, 3, 4, 2. Right? Yes, go.
I'm confused. Why didn't you put 1? So, for example, the 1.
Yeah.
Can you have a graph where you switch 4 and 5?
It wouldn't maintain color order. Right? So let me read these out. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? And these are the 5 distinct color. And so one way you can prove it to yourself is apply t hat to any edge, and you'll land on. And so if you wanted to, you could draw a graph of graphs where you could give each of these graphs would be a vertex here, and a t hat just connects the graphs. And you'll see at 5 points you get a pentagon, right? It's one skeleton of associahedra at 5 points. This doesn't matter. This is useful. This is fine. This is useful. I mean, the ability to generate quickly the graphs relevant to a particular color order is useful. Okay. I'm not going to do all 6, but when you do all 6, you get 14. Okay? And so what's the number? This is a good question. What's the number of ordered graphs at multiplicity n? You know what I mean by multiplicity, right? I mean the number of external points, right? Okay, well, it's exponential. It's a Catalan number. Okay. I'm going to leave it to you to prove it's a Catalan number. And to prove this counting holds, but I can give you a hint. Well, so let me tell you. Let me tell you a secret. It's not a secret. Something that's kind of useful. Do you guys know about the Encyclopedia of Integer Sequences? Yeah. So useful, right? So you start seeing this pattern. You go, oh, I've got a 1, and I've got 2, and I've got a 5 and a 14. I wonder if that means something. So you go to this online encyclopedia of integer sequences, and you see it's a sequence, right? And you see it's a Catalan number. You're like, oh, I wonder why. Then you look, this is great because it tells you all the other things that have this catalog number. One of the things is all the ways of triangulating a polygon, right? So this is kind of cool. I'll just mention this. So because you've maintained planarity, because you have the same order everywhere, you can go to a dual graph, right? And so you can understand all the different color orders as all the different ways of triangulating a polygon, right? So. All right, so you can take here, so there's it's called the Euler division problem. Is this useful? I don't know if this is useful. It's kind of cool. And for theories that are entirely planar, like you take your number of colors infinite, like, 3 is pretty big. You take your number of colors infinite, then you only have to worry about planar graphs, right? Even at loop level. Like, so a lot of the magic, when you hear other people, not me, when you hear other people talk about, the spectacular success of the Amplitudes program over the past 15 years, a lot of that's been in planar n equals 4. And there have been miracles in planar n equals 4. And part of it has come from appreciating the type of geometry that can show up. Okay.
Should we understand where that shape comes from?
Oh, good. This shape right here, or this shape? You should understand where this shape comes from.
Okay, yes, I think I
Okay, good. So all I did was I went to a dual space where I turned, if you like, I closed all. Oh, I drew a pentagon. I drew a pentagon. This is a pentagon, right? Okay, and I triangulated my pentagon, meaning I turned it into triangles. Right? That's what triangulation means. I could have chosen a different triangulation. I could have chosen this one, but I chose this one. All right? What I'm doing is I'm giving every loop a vertex, right? And then I'm crossing all the lines. And I get back this. Similarly, if I wanted to go from here to here, if you imagine these sum up to 0. The momentum sums up to 0. So you can have them morally reaching a point at infinity, off in the distance, without crossing any lines. So I'll just draw a crappy version of that. You see how I didn't have to cross any lines? Because it's planar. I didn't have to cross any lines, so it's actually, honestly, a planar graph. And I take every loop, including this one, and I give it a point, and then I just draw the lines, and oh, look, I've got a pentagon with this triangulation. Okay? I mean, is that useful? It helps you figure out where this number comes from. I mean, you can prove this other ways, but this was the most intuitive understanding for how to get that. But well, notice, okay, so yeah, I've got factorial upstairs, factorial downstairs. It goes exponentially, right? Let me contrast this. So let me contrast this with the total number of cubic graphs. Now remember, if you're including contact terms, if you're including contact graphs, that's more than cubic graphs. So if you assign things to cubic graphs, your problem is better, right? Unless you have no 3-point vertices, then you should stick with the smallest valence vertex you have. Good. So ordered. 1, 2, 5, 14. Unordered. Meaning the full amplitude. 1, 3, 15, 105. And it only gets worse because this goes as 2n minus 5 double factorial. So this grows factorially. This grows exponentially. Okay? So what did you gain by this? What you gained is you only have to consider a smaller subset of graphs and its gauge invariant. And you can do cuts on the smaller set of graphs and its gauge invariant. So you can build up your full prediction by considering functionally, if you do this functionally, if you keep off-shell if you keep formal polarizations and stuff like this, you only have to address one of these amplitudes. Then you get to relabel all you want to get everybody else. Okay? That's what you gain. How does this help you if you don't have a gauge theory? Well, you might have a double copy. So that's what I'm going to talk about next. Okay? So I'm not going to talk about any more graphs. If we had more time, I'd show you how you could sew these together to get loops and bigger loops. Go. Yeah.
Oh, sorry to interrupt. Really basic question. So with this program,
Yep.
are we then adding amplitudes, multiplying? Like, how do you build up to the correct number of processes or correct number of terms in the amplitude?
Good. So your full amplitude for adjoint at tree level, multiplicity m, I'm going to sum over the permutations of 2 to n minus 1. Okay? I'll have the color weight of the half ladder where, sigma 1 through sigma n minus 2. Did I count the n minus 2, n minus 1, n? Good. I can add. So the color weight, the FABCs of this, right? Ordered amplitude, 1 sigma n, where this is the permutation, right? But if I've written this down functionally, I only need to figure out what one version is, and then I get everybody else by relabeling. Yes? Okay? Good. So we saw this at 4 points. So you go back, take this very expression and go back to 4 points, where all you get to exchange are 2 and 3 for the color, and then look at what ordered amplitude has to be next to it. And you'll reproduce the discussion we had the end of last lecture for some choice of exchanging. That would be a CS and CU, right? So if you exchange CT for a CS minus CU, then you'd have what we had last time, and you'd write it like this. Okay? Good. All right. Yeah. And of course, so you can build this up with cuts and factorization at tree level, starting from small multiplicity. For theories that are protected by symmetries, there are on-shell recursion relations you can derive for those particular theories, like Yang-Mills and nonlinear sigma model and stuff like that. I'm not gonna go into that, but I just wanted to let you know that when you have theories, you can exploit your theories to go big, right, with this. And so it's something worth thinking about. Even if you love Feynman rules, the right thing to do is calculate one of these functionally and relabel it. Don't calculate everybody, okay? Good. Let me point out, this makes a huge difference at loop level, right? So if I'm going to talk about some L loop process, okay, one way of constraining all the data, make sure I've got the right answer, is to consider an L plus 1 particle cut. All right, so I'm cutting it into 2 trees, right? Where this tree has L plus 3 edges, and this tree has L plus 3 edges, and I'm sewing L plus 1 of them together. Okay? Now, let's see what happens when we've got a 6-particle tree here. So what are we talking about with a 6-particle tree? We're talking about 1, 2, 3, 4, 5, 6. So I'm talking about a 3-loop process. There's only 3 loops. Okay? If I do it with ordered trees, I've got to worry about 14 times 14 contributions. That's a lot, but I can deal with it. If I'm doing it with colored dress cuts, I've got 105 times 105. And I don't gain anything more. All the information I needed, right, for at least this particular color order is in this. And with a judicious choice of cuts, you end up touching all the topologies with one. So it's, or with a small number. So in any case, I just want to emphasize, this really does make a difference. Good. Oh, yep.
It seems like when you do this at loop level, it kind of looks like the optical theorem, but on steroids.
Yes, that's how. So that's my advisors. V. Byrne used to get out of talking about unitarity cuts by calling it the optical theorem on steroids.
Nice.
And it is related. It is related, but recall. So the optical theorem is important, and the optical theorem, I wouldn't say is supplanted by this, because it's talking about something else. It's talking about, it's talking about in a particular structural case, what's preserved and the imaginary part of amplitudes on residues. And that's still used and useful for all sorts of positivity arguments that people make. But the way I'd like you to think about this is it's a way of thinking. If I have a theory that was described by Feynman rules, it's a way of organizing the information that Feynman rules had so that you're trying to go after the maximal amount of information in any step with the minimum amount of work, trying to minimize the redundancy of your calculation. Okay, which is very different from the optical theorem. The optical theorem is really all about the unitarity of the S major, S as one, and so yeah, but it's related. You're absolutely right. Okay, I'm going to talk about double copy now. All right, now. All right, generally, for adjoint type theories, so I'm going to sum over all the cubic graphs. So this is the full, 2n minus 5 double factorial. And this is gauge invariant, right? So I'm summing over all the graphs. I'm just stressing the color of the graph. So I am not in a color basis, okay? The reason this full observable prediction is gauge invariant is because these obey certain relations, right? So you get cancellations between diagrams. These obey certain. This is what we exploited to get our gauge invariant ordered amplitudes, was by going into a basis. Yes? Gauge invariant because the color factor obey anti-symmetry and Jacobi. Yep.
So you said we're not in the color basis, but wouldn't it be easier to just go to the color basis?
Yeah, that's what we did.
Okay.
We went straight to the color basis, but I'm going in a different direction now. Okay, I'm just saying that this thing is gauge invariant because of properties of these guys. Okay. If I have something else that obey the same rules, the same algebraic rules, right? Anti-symmetry and Jacobi. I can't move up something that's solidly affixed to the wall. that a n and tilde point and tilde n. This is also gauge invariant. All right. And if n and n tilde each contain spin 1 information, talk about vectors. And what do I mean by talking about vectors? They each have one polarization per external leg, right? One, spin 1 polarization per external leg. One spin. So this guy has 2 spin 1 polarizations per external leg, right? So I'm talking about a spin 2 particle. I'm talking about gravitation. I'm talking about amplitudes in a gravitational theory. This is gauge invariant, right? If these guys obey the same rules. So I'm going to, yeah.
I know you told us that color and kinematics are in some way interchangeable, but
Good.
I don't really understand, like, conceptually how it works to switch a color weight to a kinematic weight.
What I'm going to do is I'm going to take these, I'm going to throw them away, and then I'm going to put these here. Okay. And what I'm telling you is that all I've said right now is that this is functionally spin 2, and it's gauge invariant, right? If I take any of my polarizations and I replace it with a momenta, I'll get 0, because this guy obeyed the same algebraic properties as this guy. Now, what I'll show you what I aspire to show you relatively soon is I'll show you how linearized diffeomorphism arises from gauge invariance through the double copy. And I'll do that in just a second. But I want to just talk about, these don't have to be, by the way, both spin 1. This doesn't have to be, Yang-Mills. This doesn't have to be Yang-Mills. All sorts of things. I can build so many theories out of a small number of building blocks. And this is a type of relation that is so far absolutely still obscure at the level of the action. But this is something we can definitely see in scattering amplitudes, in gauge invariant observables. So let's just talk about it for half a second. Yeah, and let me say that this isn't conjecture. This is a calculational fact. If you do this with Yang-Mills, you get tree-level graviton amplitudes for Einstein-Hilbert gravity. The theory of Einstein's general relativity, you perturb around flat space, you call that perturbation a graviton, you get those scattering amplitudes. You get graviton scattering amplitudes by doing this, by arranging your numerators so that they satisfy Jacobian antisymmetry, which they always do at 4-point. But at higher points, depending upon the gauge you chose, how the contact terms were assigned from your Feynman rules, it may not. But you can always move that information around, and it's provable you can do this to all multiplicity. You can always find a representation where your numerators, your kinematics that depend on polarizations and momenta, satisfy Jacobian antisymmetry 1-to-1 with your color factors. Okay, so is that useful? It's absolutely useful. The highest precision post-Montonian calculations for classical gravity towards next generation gravitational wave observation has been done this way, and then taking the classical limit. All right, so okay. So I'm just going to make a little table to talk about the types of theories that can show up, just to make it clear. So vector with color, I get Yang-Mills. Of course, I can have all my super partners speaking with a vector. Do phenomenologists talk about supersymmetry anymore? Is that passé? All right, so nope. Exactly. Yeah, right? So it's still a useful playground to learn. So the nice thing about supersymmetric theories is they're easier to calculate in. You'd think, something with a whole bunch of states running around would be a mess. But if you look at it the right way, they're easy to. So it's a good playground to see if universal ideas even work in the simplest case. Potentially universal ideas. If you have something you think's universal and it doesn't even work in the simple case, don't bother trying it in the complicated case, right? So Born-Infeld. All right, so if I have pions, color, pions, nonlinear sigma model. Right, and it turns out because there are only so many massless irreproducible there are only so many particles in the Wigner classification, right? There's only so many building blocks here, and then you're spanning all sorts of things to be talking about. Okay, and if you can figure out how to write higher derivative operators in terms of this, then you have ways of finding ultraviolet completions for these theories. Yes?
Are you using the word pions here the way that you've been using the word gluons?
I am. So what I mean is the kinematics for so Goldstone bosons have a universal kinematic structure at tree level. You can have whatever color group you want, but universal kinematic structure, and that's what I mean by pions.
And also, what is NLSM?
Oh, like nonlinear sigma model, chiral Lagrangian. Yeah. So I mean, it needs. So this by itself is just kinematics, right? You need the structure to get like an amplitude in an actual theory, right? Color. Remember how we came up with this sort of bi-adjoint scalar? So the only interesting thing besides giving a cubic vertex between scalars, so we could give a cubic vertex with scalars a 1, or we're able to give it like an FABC in one gauge group and an FABC in another gauge group, right? So you get the bi-adjoint scalar. All right. So, all right. What do I want to say? I want to point out something. I want to point out that to all multiplicity at tree level, if you can specify functionally your half-ladder graph. Why do I call it half-ladder? Because it's like what happens if you cut a ladder. Yeah? All right, good. So, fancier people will call it fancier things. So I think Lance calls this a multi-peripheral diagram. I'm going to call it a half-ladder. So if you can dress this functionally in a way that satisfies color kinematics, then you have everything. Let me give you an example. At 6 points, you've got something that looks like this, and you've got something that looks like this. Right? And those are the only two topologies at 6 points. Okay? But what is this? This is just a t-hat operation on this edge. I'm not sure if you can see it, but yeah, I bring these guys to pinch together, I bring these guys to pinch together, and I give an edge between. That's my t-hat. Right? Now, what is the Jacobi relation? S hat as the identity equals t hat plus u hat, Or, if you like, t hat equals s hat minus u hat. Okay? What's a u hat on this guy? It's just this. So a u hat, right? A u hat. But this is just this relabeled, right? This is just, instead of calling it 1, 2, 3, 4, 5, 6, this guy is 1, 2, 4, 3, 5, 6. All right? I just untwisted. Yeah? So you get this guy in terms of this guy minus this guy, right? So any topology that's a t hat away, or t hats, multiple t hats away from half ladders, you ultimately reduce back to half ladders if you can impose Jacobi. So if I know this functionally, I just need to know one graph at every multiplicity in a way that satisfies the duality between color and kinematics. And I've got the entire amplitude encoded there. That's an incredible reduction from 2n minus 5 double factorial, right? So it's a combination of Jacobi and automorphism symmetry for the topology that brings me down to 1 for every multiplicity. Good. I could talk about KLT. I'm not going to. Have people heard about KLT? Wait, go.
Thanks. So I see that the half ladder with 6 external legs has to have 4 vertices. But what about like 6 external legs with other numbers of vertices?
Right, and so we're gonna assign all our contact terms to cubic graphs, and this works even for pions, even for the nonlinear sigma model. I'll just show you. Where am I going to show? I'll show you that working right here. Right here. So nonlinear sigma model, 1, 2, 3, 4. Now, what you may recall is it's derivatively coupled. So there's no 3-point interaction. There's just a 4-point and a 6-point and an 8-point and a 10-point, right? And the coefficients are carefully tuned for an Adler zero. So spectacularly good behavior, right? So good. So what is the ordered amplitude? The ordered amplitude for pions. So pions have color weight and adjoins. What's the ordered amplitude for something like this? It's proportional to u. It's proportional to k1 plus k3 squared. Okay? Good. But I claim that I can write it in a color dual fashion. And so what's the numerator for this for pions? It's just going to be s t minus u. A little bit later, I'll show you how you can see this. When I start talking about effective field theories, I'll show you how you can see that this is actually color dual. But this is the dressing. What I want you to notice is the s sitting in front. All right? So this ordered amplitude should be ns over s plus nt over t equals s over s t minus u plus, so to get this guy, I just relabel, right? And it's just swapping s and t's. So it's t s minus u over t. Okay? So equals t plus s minus 2u. This is minus u. Minus 2u equals 3u. Okay? So if I'd divided this by 3, I'd land exactly on u. All right? So you can always encode effective field theories that are contact terms, higher derivative operator, always. For the theories that you can make color dual, you can always assign it to cubic graphs and talk about things this way. Okay? Question? Yeah. So so if you know trees, you know loops. So there's a tremendous reduction in complexity. Again, there are only so many complete loop level calculations that have ever been done. At 3 loops in the maximally supersymmetric Yang-Mills case, there are 12 topologies. You get all of them from Jacobian antisymmetry on 1. I mean, when you integrate, I mean, you have to do all the labels of those topologies, but there's 12 distinct topologies. At 4 loops, there's something like 80 some odd topologies, and they can all come from Jacobi from 1 non-planar graph. At 5 loops, we don't know how to write down a color dual representation. But it looks like if we could, and this is still an open question, but it algebraically, there's some 900 some odd graphs, and you get them in terms of 3 graphs. Yeah. So now, what's the tension? What's the tension at 5 loops? There's a question for ask me about it in Slack. The short answer is the ansatz. How do you find these color dual representations at loop level? You write down an ansatz, and you apply cuts, and you apply whatever symmetries you care about. So the thing is, we can't give we don't have the computational power to give a spanning ansatz at 5 loops. The ansatz we've tried, we can satisfy color kinematics, but we haven't been able to satisfy the cuts. But it's not a proof that you can't do it, because there's all sorts of things we could be doing. And it's just so there's a lot of active research towards trying to understand more constructive ways of building color kinematics representations than ansatz. And I will try to get to an example of that in a few minutes. That was a good question. Good. Did I answer? Have I answered all questions on the table? All right. So what I will say is from this notion, you can write a vector of ordered amplitudes as some sort of matrix of propagators with signs, times some vector of numerators, right? So at 4 points, so a 1, 2, 3, 4, I get with NS, NT, right? So it would be like a 1, 1, right? Gives me 1 over S, 1 over T. All right, then 1, 3, 2, 4, some other set of propagators, with appropriate Jacobi combination of NS and NT to get NU, right? All I'm saying is that there's, some set of propagators, some denominator matrix here that lets you take your set of numerators, to your ordered amplitudes. What this means is if you go to a basis of your n minus 2 factorial half ladders, I can pseudo-invert this matrix to get my n's in terms of ordered amplitudes. Okay? Which means I can plug things into a double copy like this and end up with some kernel matrix which takes vectors of ordered amplitudes and turns it into a double copy theory, right? So Yang-Mills would be just color dressed amplitudes, so color stripped by adjoint scalars with Yang-Mills. This kernel is called a KLT kernel, right? And this has a venerable history. This was first discovered in string theory in the 80s, and it was very mysterious, but still useful for calculation, for decades to come. People only know how to do this at tree level. And it can be a little confusing. But we understand how to generate these for all sorts of color dual theories, whether things are in the adjoint or fundamental or what have you. We now know how to build these. All right, that's all I'm going to say about KLT right now. But this can be spectacularly useful if you're sitting on a bunch of ordered amplitudes and you don't want to find Jacobi satisfying representations, but you still want to double copy. Good. So I've got 20 minutes left, and both will appear in my notes when I put them. So I'm gonna have a poll. Who wants to see a quick proof of linearized diffeomorphism arising from gauge invariance, or who wants to hear me start talking about sprinkling Ks to get higher derivative operators in amplitudes? So raise your hand if you want to see linearized diffeomorphism arise from double copy.
Which one do you think would be easier to follow for few people?
I think both. But and who wants to see? You know what? I'll try to do both. Let me try to do both. All right. I'll give a taste of both. And right, the linearized diffeomorphism stuff's actually pretty easy. So good. So all right, so what is a linearized gauge transform? Right? There'll be some E mu associated with P going to E mu P plus P mu. Right? And this has to leave our amplitude unchanged. Right? If this amplitude is to be gauge invariant, this has to leave our amplitude unchanged. So every numerator will go to itself plus, some change where the change is the numerator evaluated, where the epsilon goes to the p, right? Yeah? Now, if individual numerators were gauge invariant, right, then this would be 0. But individual numerators aren't gauge invariant, right? But the fact that this is gauge invariant, the amplitude is gauge invariant. This means that this is 0. Yeah? Okay. Well, this relies on the algebraic properties of this. This is just what I said before. Now, this error relies on the algebraic properties of this. I'm gonna write it. It's important enough I'll write it. Relies on algebraic properties not just the numbers, right? Not just whatever numbers associated with whatever random gauge group we were calculating in. Yeah. All right. So if we have some color dual numerators, kinematic numerators, and I'll annotate them with a halo because they're angelic, right? They satisfy color kinematics and double copy, and also distinguish with the tilde. Then what?
Can you do the
Yes. Yes, I have done the halo in LaTeX. I can send you. Send me a message on Slack. All right. So let's consider the double copy. This is invariant under linearized gauge transforms of Ni as, yep. Right? I haven't done anything interesting. I'm just saying if this satisfies the same algebraic properties of these C's, then this has to be 0 too. Okay? Yeah?
What do you mean by linearized?
Linearized gauge, yeah. I'm just going to add momentum to this, yeah? Good. All right, so. Well, I'm erasing. I should say, I said, oh, what's the use of this? For planar theories, having color dual representations has been incredibly instructive. So we learned about a new symmetry in the large N limit for maximally supersymmetric Yang-Mills by looking at color graphs. Krachemsky and Hen and Sakajev discovered that this theory had a dual conformal symmetry that is in addition to the conformal symmetry that N equals 4 super Yang-Mills says. So I shouldn't bad talk going to dual graphs. Dual graphs are great. Gravitons. Gravitons have a polarization. And what do they satisfy, right? What do the graviton polarizations satisfy? They satisfy transitivity. Transitivity. Right? You dot it with a P, you get 0. Yeah? And they satisfy tracelessness. Tracelessness. Okay? So what is a linearized diffeomorphism look like? It looks like epsilon mu nu rho going to nu rho plus p u q nu symmetrized. And what's q? It's some null vector that's null with respect to v. Q's some reference null vector. All right. This is what linearized diffeomorphism invariance looks like. And let's recall that we can always write our graviton polarizations as symmetrization of vector polarizations. Right, this is something we discussed 2 lectures ago. Yeah, you can get higher spin by, just the level of even the free wave function. Yes.
Just what is that notation where you're putting the?
Oh, yeah, I'm symmetrizing. So I'm going to symmetrize p mu k nu plus p nu k mu. So symmetrization. That's one of the most frustrating things about dealing with gravitons is the number of times you have to write the exact same thing, but with the indices swapped, right? Yeah, and that's why like the off-shell 3-point graviton rule, if you expand it all out, has something like 171 terms. It's because of all the different ways of symmetrizing over the indices. Okay, good. So, all right. Let's consider n graviton. The numerator for my graviton amplitude as 2 copies of these kinematic weights, like I was telling you about the double copy, right? So you'd write so what I'm going to do is I'm going to have angelic representations for both, right? So they both satisfy color kinematics, yeah? And this I'll call my graviton numerator. Okay? So the claim is that n graviton under a linearized diffeomorphism goes to right? This is for 8 unchanged. QP. All I've done is plug this in to here. Yeah? Via this. Good. So yeah. Now, what we have to ask ourselves is what happens now if, how do I want to say this? Yeah. So if these guys are angelic, right, then all of the gauge transforms vanish, right?
Thanks. Yeah. I don't know if this is a fair question or not,
Yeah.
but is there some tangible physics we can connect this to?
You mean besides the scattering of gravitons?
Well, like,
I mean, no. I mean, like observing gravitational waves from or like the perihelion shift of Mercury, or
more like just like what is this scattering that we're talking about? What's happening with these polarizations?
oh, so what? Good. So why do you care? Okay. So I made a claim. What did I do? I made a claim that I was talking about that I was actually talking about scattering amplitudes in a gravitational theory, right? What do we have? two things. First, we need to be talking about spin 2 for that to be true. And it's obviously spin 2. But it also has to respect diffeomorphism invariance, or it's not an amplitude. So is it still a scattering amplitude? Or have I just created some weird operator that happens to be spin 2, but that's not gauge invariant in this new theory? And what does gauge invariance mean for gravity? It means diffeomorphism invariance. So the point of this is to show you that this operator is actually an amplitude. Okay, does that make sense? Okay, and so, I've got 5 minutes. All right, you know what I'm going to do? So you can plug this into there and see in each case, right? Because what is this reference momenta doing? The whole thing about this reference momenta is it satisfies the same property of a polarization, right? It dots to 0, right? That's what our formal polarizations do for a living. So it's a lot like a new type of polarization, okay? So all the same arguments hold through, right? And you leave that operator invariant. The question is, what happens if I did this when one of these guys isn't angelic? But it's possible to convince yourself with a few more minutes that I'm not going to do, that any deviation from this vanishes along this. And I'll give you a reference in Slack where you can see the rest of the argument. Okay, I think you get the spirit of the argument at least, yes? All right, so in the last 5 minutes, let me talk a little bit about what we've been learning about how you can classify higher derivative operators in gauge theories and gravity theories and all sorts of theories using color kinematics, and something really fun we've discovered, which lets us build color dual effective operators constructively without having to apply an ever increasing horrible ansatz at higher orders in mass dimension, which is the same sort of nightmare that we deal with loop level, right? But we found something constructive, and one of our aspirations is being able to do these sort of constructive operations at loop level as well. All right, so I'm not going to have time to give a bananas amount of details, but let me just tell you something that's true. Is that at every multiplicity, you can define a permutation invariant composition. Between adjoint type numerators and what do I mean by a permutation invariant composition? I mean if I have an operator P that I've defined as n permutation invariant composition and twiddle, all right, they're angelic because they satisfy Jacobian antisymmetry, then this guy, then P, is invariant under all relabelings. Okay? Let me give you an example at 4 points. Okay? What is this? You sum over all channels, and it's permutation invariant. All right? It's kind of trivial, but it's true. Okay? Good. Let me tell you something cooler, even cooler. I can define an adjoint composition that takes, A equals and A satisfies Jacobian antisymmetry. Okay, I'll tell you what this is at 4 points. The S channel is NT minus NU. Okay, so if I have something that satisfies Jacobian antisymmetry, and I define the S channel from two objects by I can take the product of T's and subtracting the product of U's. And this object satisfies Jacobian antisymmetry. Okay? And you can do this at higher multiplicity. I've got 1 minute. Okay, so this is the punchline. All right, the punchline is you can define something that's just in terms of scalars, right? T minus U, so S hat. S is T minus U. This is a covariantized free scalar. This is what happens when you have a free scalar, d phi squared. I turn the little d to a big D. I let it speak via glue. 4 points, satisfies Jacobian antisymmetry, and the kinematic weight is T minus U. It's linear in Mandelstams. What happens when I compose it with itself? I get something quadratic in Mandelstams. I compose that with something linear, 3, 4, 5. I've got a ladder I can climb all the way up to the UV, because what is this? This is a way of distributing Ks. This is a way of higher derivative operators. But what's even better is this thing closes at every multiplicity. This climbing the ladder closes up to permutation invariance very quickly. So if I do the second order, if I say what's this simple scalar composed with itself, the covariantized free scalar composed with itself, I get S, T minus U. I get the nonlinear sigma model we were talking about earlier. If I do this with this, I get something that's spanned by these two multiplied by permutation invariance, right? So my ladder closes up to permutation invariance very quickly. I can compose these with color weights without messing up my gauge invariant structure at all for Yang-Mills or all other tensor structures. There's only a finite number of tensor structures that satisfy adjoint. With this, you can build all gauge invariant color dual effective operators constructively. And you can expose this structure all the way to the UV in string theory, both open and closed string theory, bosonic and supersymmetric. You can see this structure. All right, with that, I'm done. I went 2 minutes over.